Previously, we covered simple linear regression modeling with the Boston housing data. Now, we want to proceed now to the topic of robust regression in this video. One of the rationale for moving away from simple linear regression is that linear regression in its current form is heavily impacted by the presence of outliers. Outliers can really completely destroy the linear regression fit. So it has a big impact on the estimated coefficient. The coefficient could be intercept, it could be the slope as well, but it doesn't matter. Basically, it actually will be impacted heavily by outliers. Now, there are a lot of statistical tests that can be used to detect these outliers, typically residual regressions, but we won't cover it here. And the primary reason is that we can use a different algorithm that I'm going to demonstrate here to actually model your data without in a simplistic or fairly quick manner. One of the key things to remember is that data science require an understanding of the domain and that you are modeling in. So domain expertise is very important. As a result, outliers detection require a good understanding of the domain that they operate in. Okay, so let me just demonstrate a little bit of how linear regression can be heavily impacted by outliers. I've given this link here, and basically this is the applets that's provided by this website. I've simulated 100 points, as you can observe here. It shows the scatter plots, which shows obviously the form. It's fairly condensed here, but it also shows the direction and the actual strength of the relationship between the two quantitative variables, the x here and also the y here. So if we show the mean xy lines, that then you know that it's actually basically here. So if we draw the least square line, that's basically the linear regression here, and if we show the residual, that's basically what it looks like. Now, just wanted to show you, if I take a point like this, just pay attention to the correlation coefficient here, 9.561, and observe what happened to the line, the blue line, as well as the correlation coefficient. So as I drag, notice that the line is starting to tilt. The correlation coefficient is also tilting, and this is just one single point can actually have such a major impact on the overall scheme of things. So imagine if you have a few of these, they will definitely make a major impact. It went from earlier was 99, so let me just remove there. It was 1, 2, 3. It was about I recall it's 80 something. I'm much higher than that, but 8620, if I add 3 dots here, it drops down to 63, and that clearly shows you how heavily this whole thing is impacted by the outliers. So that's one thing to keep in mind of how severe linear regression can be impacted by outliers. So I encourage you to play with this. This link has already been provided here. So convince yourself that linear regression is heavily impacted and influenced by outliers. So just again refresh our memory in terms of the information that we have, and we're going to go into random sample consensus algorithm. The link is also provided here to the scikit-learn library. Basically, what is RANSAC? The RANSAC algorithm fits a model from random subsets of inliers from the complete data sets. So instead of working with the whole data sets, it automatically sample and try to identify the outlier and exclude them from the actual modeling itself. So the algorithm itself, with each iterations, perform the following steps. It selects a random number of samples to be inliers and fit the model. So we need to actually set the minimum sample, min samples here, random samples from the original data, and check whether the set of data is also valid. And the second thing we need to do is fit a model to the random subset. Okay, so that's really the step 1 and step 2 here. And we also check whether the estimated model is valid or not. The third step then is to classify all data as inliers or outliers by calculating the residuals to be estimated model. And basically that estimated model is the base estimator predict minus the actual observed value y, and all data samples with absolute residual smaller than the residual threshold are considered as inliers. So basically when we were looking at this part here, I'll show the residual. So those, let's just say we have a defined distance of roughly about 1, let's just say this is 3, then this will be considered as outlier. And this is 1.5, so outlier, outlier, outlier. That's basically how that is calculated. Okay, so but you need to define the residual threshold yourself. Save the fitted model as the best model if the number of inlier samples is maximal. In case the current estimated model has the same number of inliers, it is only considered as the best model if it has better scores. Okay, so we are going to use average number or medium number of room as our predictor. X, again, we need to reshape this into a matrix format, and the y here being our dependent is the median value. So store that from scikit-learn. We will import the ransack regressor, instantiate the model, and fit our data. Notice I haven't defined any variables. We are just using the default numbers here. And from the ransack inlier mask, we store them into this variable, and from the numpy logical not, anything that is not the inlier mask will be outlier. Right, the next thing is that we draw a line, arrange basically from 3 to 10 with a step of 1, and we conduct our predict, all right, using the model that we fitted. And what we're using is basically the numbers here from between the range of 3 to 10. All right, so let me just show you what is this, because in case you're not familiar with NumPy, and this is basically what it looks like. So basically from 3 to 10 with a step of 1, but not including 10. All right, so we fitted it, and we basically have lin underscore y underscore ransack. Okay, so let's just plot it out and see what it actually looks like. We're plotting the figure. Basically it's a scatter diagram. We are plotting both the inlier and also the outlier. The inlier will be in blue, the outlier will be in brown. We're also plotting our best fit line, which is this line here, lin x, and lin y is what we estimated using the ransack. The line y, sorry. The color being red, and the x label is the average number of rooms per dwelling, and y label being the median value of owner-occupied homes in the thousands, and store our legend descriptions to the upper left corner. And let's plot it out and see what this looks like. Okay, so what do you see here? You see the blue, okay, as denoted here, are the inliers. The brown, which are all of these dots here, are the outliers. And the red is our best fit line. Okay, now if we just take the model, let's just add 2 lines here. Okay, and look at our coefficient. It's 7.21. Let's repeat the same. Again, estimated. And the intercept is minus 22. Let's refresh our memory from previously what the numbers were. It was 9.1 and minus 34. And clearly that's actually quite different from 7.2 is versus 9 point something, minus 30 something versus minus 22 something. Okay, that's really the end of this video on how to use robust regression using specifically the RANSAC algorithm to perform this algorithm modeling. For the remaining part of the video, I'd like you to actually take a moment, instead of running it on RM and versus the median house prices, try it on the LSTAT, okay, the percentage of lower income versus the lower status of the population versus the median value, and see what you get. So pause now, take a few moments and try this out until you are familiar with the robust regression using RANSAC algorithm. Okay, how did you find that exercise? I hope you actually tried out using the LSTAT feature and see what it looks like when you actually try to model it to using the RANSAC regressions. Now this is what I've done. Let me change that to code and plot that out and just to visualize. Alright, so let's just change this to upper right, because that's where everything is. Okay, looking at this, what do you see? So you have the brown are all the outliers, the blue are the actual inliers, and that's really the purpose of that exercise, to actually get you to be familiar with the using RANSAC regression. I hope really that you tried it out and you've got something similar. And just to summarize what we have learned here is that we've learned first and foremost that linear regression can be greatly affected by outliers. Number two, what we've learned here is the process of using the RANSAC regression. Now the beauty is that because we are using the scikit-learn library, you probably noticed by now that we just repeat the 5 steps, except that we are applying it using a slightly different model. Ultimately, the whole process is exactly the same. So now that you've learned it, you can actually apply this same set of skills and same set of toolbox that you have right now. We will continue to increase the number of tools that is added into your toolbox, and to allow you to model any situation or any data sets that you are working with. Having done all that, the next part now that we're going to go into is to evaluate your model. Up to this point, we've done a lot of modeling, but what we do not know is that which model is actually the best. That's really the purpose of performance evaluation, or evaluation of the model, to compare and contrast the models that we've been using to actually tackle our data. And the next part really is to evaluate the regression model from the different approaches, and that's really a crucial part of building a system for predictive modeling. So I look forward to seeing you in the next video.